Conversely, how to get the logic expression from the true value table? There are also 3 steps. The first step is to find all AND combinations when y is 1. In the true value table, we can find these combinations output is 1, which means A and B not and C can provide 1. Similarly, A and B and C not provides 1. A and B and C provides 1. From the true value table, we can know that there's only 3 combinations outputs to be 1. The second step is to combine them with OR operator, which means A and B not and C plus A and B and C not plus A and B and C equals Y. Why? Firstly, when any of them is 1, the output is 1. It accords with the result of the 3, 1. Secondly, only if these 3 combinations are 1, they are 1 outputs. From the 2 reasons, the expression must be equal to 1. The third step is to simplify it to get its simplest logic expression. The simplification from this logic expression to this logic expression will be introduced in the digital electronic course. Next, we discuss the common logic gates. The first one is a buffer, whose input equals the output. The second is the inverter. The inverter symbol is the buffer's output with a circle. The inverter is corresponding to the logic expression NOT. The following ones are AND and NAND. The NAND gate's output has a circle which is different from AND gate. The following ones are OR and NOR. I need to point out that the 3 basic logic expressions discussed above are corresponding to the inverter, the AND, and the OR gate. But in the following lectures, you will find that the inverter, the NAND, and the NOR gate are simplest to manufacture in the industry. You may find the reason in the following lectures. After all, there are 6 common logic gates. Then we discuss the 4th question. If you have a logic expression, how to implement it with the logic gates? Take the expression that y equals A and B or C as an example. It's obvious that an OR gate is necessary. Its output and A is Y. You can use logic gates to create any complicated logic expression. At last, we will introduce how to realize the digital operation with the logic expression or the true value table. We've solved how to precisely represent the value of a signal with a binary code. If we can realize a very simple digital operation with the logic gates or the logic expressions, then we can realize any complicated digital operation step by step. We take the half-ender as an example. Let's solve 1 plus 1 with a binary system. Their sum is 0 and the carry is 1. This is the sum and this is the carry. We all know how to end. How to realize it with the true value table or the logic gates or the logic operation? Suppose this is the input X, this is the input Y, this is the output S, and this is another output C. Now, we write the true value table based on the original addition operation. Makes the table firstly. Write down the inputs x and y and the outputs s and c. Write all the combinations of the inputs. Then we find the corresponding outputs s and c. If x, y are both 0, then s is 0 and c is 0. If x is 0 and y is 1, then s is 1 and c is 0. If x is 1 and y is 0, then s is 1 and c is 0. If x is 1 and y is 1, then s is 0 and c is 1. If we suppose x, y are two inputs and s is the output, do you know how to represent s with a logic expression of x and y? Based on the previous discussion, you may find s equals x and y naught plus x naught y. Similarly, c can be represented with a logic expression of x and y. C equals x and y. As we've discussed above, we can implement the sum and the carry with the logic gates. Thus, you can realize the half-ender with the logic gates. Based on the half-ender, we can realize the full-ender. What is a full-ender? It has three inputs, which are the current x, current y, and the carry from the lower bit. Define the current bit as I. It has two inputs, the sum of the current bit and the carry. It has two outputs, the sum of the current bit and the carry to the I plus 1 bit. It's a logic system with three inputs and two outputs. You may think about how to realize a full-ender since you've implemented a half-ender. Furthermore, how to realize a 4-bit ender based on a full-ender? It's not difficult to realize them if you understand this lecture. Okay, this is the end of this lecture.